The predictable path, unlocking the power of functional programming. Chapter 1, The Predictable Path begins, an introduction to functional thinking. Every journey begins with a first step, and our path into the world of functional programming is no different. Perhaps you've heard the term functional programming whispered in technical circles, or maybe you've encountered it as a buzzword in a job description. Whatever your reason for being here, prepare to challenge some common assumptions about how software is built. Functional programming, or FP as it's often abbreviated, isn't just another programming language. It's a profound shift in mindset, a different way of thinking about problems and solutions. Beyond the code. Understanding programming paradigms. Before we dive deep, let's zoom out for a moment. Programming isn't a monolithic activity. Just like there are different schools of thought in architecture or philosophy, there are different programming paradigms, fundamental styles, or approaches to building software. You're likely familiar with some of these already. Perhaps you've written imperative code where you give the computer a precise, step-by-step list of instructions. Do this, then do that, then change this variable, then loop 5 times. It's like writing a detailed cooking recipe, specifying every action. Take the flour, pour it into the bowl, add water, stir until smooth. Then there's object-oriented programming, OOP, which organizes code around objects, bundles of data, and the operations that act on that data. Think of it like building a world out of self-contained, interconnected machines. A car object might have data like its color and speed, and operations like accelerate or brake. This paradigm often emphasizes mutable state, meaning the data inside an object can change over time. Your car object's speed will change as it accelerates. Now, imagine a different approach. What if, instead of telling the computer how to do something, we focused on what we want to achieve? What if we treated computer programs more like mathematical functions, where inputs always lead to predictable outputs and nothing else changes? This is the essence of functional programming. The aha moment. What problem does FP solve? So, why would we need yet another way of programming? The answer lies in the increasing complexity of modern software. As systems grow larger, more interconnected, and more demanding, maintaining them becomes a monumental challenge. Bugs creep in, unexpected behaviors emerge, and making changes becomes a terrifying gamble. Consider a multitasking application on your computer. Multiple parts of the program might try to access and modify the same piece of shared data simultaneously. Imagine 2 chefs in a small kitchen, both reaching for the same bag of flour at the exact same time. Chaos, right? In software, this leads to insidious race conditions and unpredictable bugs that are notoriously difficult to track down. Traditional programming often grapples with managing state, the collective memory and values of all variables in a program, and coordinating changes to that state. This is where a lot of the complexity and a significant portion of bugs originate. This is precisely where functional programming offers a compelling alternative. At its heart, FP aims to build software by composing pure functions, functions that, much like mathematical functions, always produce the same output for the same input and have no side effects. They don't change anything outside themselves, they don't depend on hidden external factors, and they don't cause unexpected chaos. The pillars of predictability, high-level overview. While we'll explore these concepts in depth in upcoming chapters, it's helpful to touch upon the core tenets of functional programming right away. Pure functions. They are the bedrock. Given the same inputs, a pure function will always produce the same output, without altering anything in the outside world. It's like a scientific experiment you can reliably repeat with consistent results. Immutability. Data, once created, cannot be changed. Instead of altering existing data, you create new data based on the old. This might sound counterintuitive, but it's a powerful way to eliminate entire classes of bugs related to unexpected modifications. Functions as first-class citizens. In FP, functions are treated as regular values. You can pass them around like numbers or strings, assign them to variables, and return them from other functions. This flexibility allows for incredibly powerful and elegant ways to compose software. The benefits of the predictable path, why functional programming matters. Embracing these principles leads to a cascade of benefits that directly address the challenges of modern software development. Reliability and predictability. Because pure functions always behave the same way, and data doesn't unexpectedly change, your programs become inherently more predictable. Bugs become easier to prevent and track down. Easier testing. Each pure function can be tested in isolation, like a self-contained unit. You don't need to set up complex environments or worry about the order of operations, just provide inputs and check the outputs. This makes rigorous testing much simpler. Concurrency and parallelism. With immutable data and pure functions, race conditions virtually disappear. Imagine those two chefs from before, but now they each have their own identical bag of flour. They can work completely independently without interfering with each other. This makes writing software that can safely utilize multiple processor cores much easier. Modularity and reusability. Small, pure functions are like perfectly crafted Lego bricks. They snap together predictably, allowing you to build complex systems from simple, well-understood parts. This promotes code reuse and makes systems easier to understand and maintain. Conciseness and expressiveness. Functional code often expresses what you want to achieve rather than how to achieve it, leading to more compact and readable solutions. Setting expectations for this journey. This book is designed for anyone curious about functional programming, regardless of your prior experience. We won't be diving into the arcane syntax of specific functional languages like Haskell or Scala. Instead, we'll focus on the universal concepts and principles that underpin functional programming, illustrating them with clear explanations and real-world analogies. Think of this as learning the fundamentals of driving before getting behind the wheel of a specific car model. By the end of this book, you'll not only understand what functional programming is, but you'll also grasp why so many developers are embracing its power to build more robust, maintainable, and predictable software systems. So let's step onto the predictable path together. Chapter 2, The Cornerstone, Pure Functions and Predictable Outcomes. If functional programming were a building, its very foundation would be the concept of the pure function. This idea, deceptively simple on the surface, is a powerful tool that, once understood, unlocks a world of predictability and reliability in your software. Forget about complex architectures and intricate object hierarchies for a moment. Let's strip programming back to its essence: inputs, a process, and outputs. What makes a function pure? Imagine a calculator. When you press 5, then plus, then 3, then equals, you consistently get 8. If you do it again, you get 8 again. The calculator doesn't suddenly give you 9 because the battery is low, or 12 because it remembered the previous calculation. It just gives you the correct result based on your inputs. That's the essence of a pure function. Formally, a pure function adheres to two strict rules: deterministic output. Given the same input, it will always produce the same output every single time. It doesn't matter when you call it, where it's called from, or what else is happening in your program. The result is consistently predictable. No side effects. It does not cause any observable changes to anything outside its own scope. It doesn't modify external variables, print to the console, write to a database, make network requests, or change the state of the operating system. It simply takes inputs and returns an output. Let's illustrate with an analogy. Analogy, the vending machine of logic. Think of a pure function as a perfectly engineered vending machine. You put in a specific amount of money, your input. You press a specific button for a particular snack, also part of your input. Regardless of how many times you do this, or who else uses the machine, you will always get the exact same snack for the same input. This demonstrates deterministic output. Crucially, the vending machine doesn't affect anything else in the room. It doesn't suddenly make the lights flicker, change the temperature, or send a text message to your friend. It just dispenses the snack. This demonstrates no side effects. Now, imagine a non-pure vending machine. You put in your money and press the button. Sometimes you get your snack, sometimes it dispenses a random item, sometimes it charges your credit card twice, and sometimes it reboots the entire power grid for the building. This is what programming with rampant side effects can feel like: unpredictable, hard to debug, and potentially chaotic. Examples of side effects and why they're problematic. To fully appreciate pure functions, it's helpful to understand what side effects are and why they can be tricky. Modifying external variables. If a function changes a variable that exists outside its own boundaries, it's causing a side effect. This makes it hard to reason about the state of your program, as any function could potentially alter shared data. Problem: imagine a global total score variable. If multiple functions can increment or decrement it, debugging becomes a nightmare. Did this function add 10 or 20? When did this happen? Input-output operations, I/O. Printing to a console, writing to a file, reading from a database, making a web request. While essential for any useful program, these are classic side effects. Problem: if a calculation function also prints to the console, testing it becomes harder. You're not just checking the calculation, but also what it printed. What if it prints different debug messages based on timing? Modifying function arguments, in-place mutation. If you pass a list or an object to a function, and that function directly changes the original list or object, that's a side effect. Problem: you pass a customer's order to a process order function. If that function subtly changes the original order object, another part of your program expecting the original might receive a corrupted version without realizing it was modified. Generating random numbers. Calling a random number generator directly within a function makes it non-deterministic. Problem: a function that rolls dice, generating random numbers, will not give the same output on identical inputs, making it difficult to test or reliably use in simulations. Accessing system time date. Similar to random numbers, the current time changes, making a function dependent on it non-deterministic. The immediate benefits of pure functions. Now that we understand what pure functions are, let's explore their powerful advantages. Testability. This is perhaps the most immediate and profound benefit. A pure function is incredibly easy to test. You simply provide an input, call the function, and check if the output is what you expect. You don't need to mock external systems, set up complex test environments, or worry about the function's internal state. It's like testing a mathematical formula. Square 5 should always be 25. Predictability. Because pure functions are deterministic, you can always predict their behavior. This makes reasoning about your code much simpler. If a bug occurs, you can narrow down the possibilities because you know how specific parts of your code should behave. Concurrency and parallelism. This is a huge win in today's multi-core world. If a function doesn't depend on or modify anything outside itself, you can confidently run it in parallel across multiple processing units without fear of race conditions or unexpected data corruption. Each execution is totally self-contained. It's like having multiple copies of that perfect vending machine, each operating independently without affecting the others. Referential transparency. This is a fancy term that simply means you can replace a call to a pure function with its result, and the program's behavior won't change. For example, if multiply bitwo 5 always returns 10, you can literally replace multiply bitwo 5 with 10 in your code, and the program will still work the same. This is crucial for optimizations, code reasoning, and understanding. Caching and memoization. Because pure functions always produce the same output for the same input, you can easily cache their results. If you call calculate complex value x once and get y, you can store this x-y pair. The next time calculate complex value x is called, you can simply return y from the cache without re-executing the potentially expensive function. Pure functions in practice, conceptual. While we'll avoid specific code examples, let's think conceptually. A pure calculation, a function that takes two numbers and returns their sum. It doesn't print anything, it doesn't store the sum in a global variable, it just gives you the sum. An impure calculation, a function that takes two numbers, prints them to the screen, adds them, and then stores the result in a variable called last result that any other function can access. The second example is harder to rely on. What if last result was already set by another function? What if the printing fails? The first example, the pure one, simplifies everything. The reality of side effects. The boundaries approach. Of course, real-world programs must have side effects. A program that doesn't interact with the user, save data, or communicate with other systems is useless. the functional programming approach isn't to eliminate all side effects, but to contain them. Think of it like building a house. The dirty work digging the foundation, mixing cement happens outside the pristine finished living spaces. Similarly, in functional programming, you aim to keep the core logic of your application as pure as possible, isolating the necessary side effects to the edges or boundaries of your system. You might have pure functions that represent data transformations, and then other, less pure, functions that handle interactions with the outside world, like reading user input or writing to a database. This separation makes your core logic highly reliable and easy to work with, while still allowing your program to perform useful tasks. We'll delve deeper into managing side effects in a later chapter. For now, understand that pure functions are the bedrock. They are the perfectly crafted, predictable components that you can trust implicitly. As we build upon this foundation in the next chapters, you'll see how these fundamental building blocks combine to create amazingly robust and comprehensible software. Chapter 3, Immutability, the unchanging foundation of reliability. In the previous chapter, we explored pure functions, which are critical for predictable outcomes because they don't cause side effects. Hand in hand with pure functions, forming another cornerstone of functional programming, is the concept of immutability. If pure functions are about not changing the world outside, immutability is about not changing data once it's created. This idea often feels counterintuitive to developers accustomed to traditional programming styles, where altering variables and updating data structures in place is commonplace. We constantly increment a counter, update a user's address, or pop an item from a list. But what if we didn't? What if, instead of changing something, we always created a new version, mutable versus immutable data? A tale of two records. Let's clarify what we mean by mutable and immutable. Mutable data, data that can be changed after it's created. Once you define a variable or a piece of data, you can modify its internal parts or its value directly. Analogy, think of a whiteboard. You write something on it, and then you can erase part of it and write something new in its place. The whiteboard is a single entity whose content can be continuously altered. Immutable data. Data that, once created, cannot be changed. If you need to make a change, you actually create a new copy of the data with the desired modification, leaving the original untouched. Analogy, think of a photograph. Once taken, the image on that specific photographic print is fixed. If you want to modify it, you don't alter the original print. You make a new print that has been digitally altered, or you take a new photograph entirely. The original remains as it was. Much of traditional programming, particularly object-oriented and imperative styles, heavily relies on mutable data. We represent a user's profile as an object, and then we might directly update its email or address fields. We have a list of tasks, and we add or remove tasks directly from that list. This direct manipulation of existing data is called mutation. Why immutability? The case for unchanging foundations. At first glance, immutability might seem inefficient or overly complicated. Why create new copies when you can just update in place? The answer lies in the profound benefits it brings to software reliability, clarity, and concurrency, eliminating unexpected side effects. This is the most direct link to our previous discussion on pure functions. If data is immutable, a function passed that data cannot change it inadvertently. Your functions receive snapshots of data, not live objects that can be secretly altered by another part of the program. This drastically reduces a common source of bugs, where one part of your code modifies data that another part of your code is still relying on. Problem: imagine our process order function from Chapter 2. If it modifies the original order object, e.g., changes the quantity of an item, and another function is still working with that original idea of the order, you can get subtle, hard-to-trace bugs. With immutability, process order would return a new order object representing the updated state, leaving the original untouched and preventing confusion. Concurrency without headaches. This is where immutability truly shines in modern software. In a multi-threaded or multi-core environment, if two parts of your program try to modify the same piece of shared mutable data simultaneously, you get a race condition. One thread might overwrite the changes of another, leading to corrupt or inconsistent data. Debugging these issues is notoriously difficult. With immutable data, this problem simply vanishes. If data cannot be changed, there's no way for two threads to interfere with each other's modifications. Each thread can work with its own snapshot of the data, confident that it won't be unexpectedly altered by another thread. It's like everyone having their own personal, permanent copies of the project blueprints, rather than trying to draw on a single, shared, erasable blueprint. Easier debugging and reasoning. When data is mutable, the state of your program can change at any point an operation occurs. To understand a bug, you might have to trace the precise sequence of operations that led to a particular variable having a particular value. This can be complex and time-consuming. With immutable data, the flow of information is much clearer. Each change creates a new version, giving you a clear history. If a bug occurs, you know exactly how each new version was derived, making it easier to pinpoint where an incorrect transformation occurred. It's like having an unalterable financial ledger where every transaction is a new entry, giving you a perfect audit trail. Simpler undo-redo mechanisms. Because you're always creating new versions of data, implementing undo or redo functionality conceptually becomes much simpler. You essentially just revert to a previous version of your data structure. You don't have to carefully track how to unmutate something. Performance optimizations behind the scenes. While creating new copies might sound inefficient, functional programming languages and libraries are optimized to handle this cleverly. Techniques like persistent data structures allow new versions to share large portions of the original data in memory, making copy operations very efficient. You, as the developer, get the benefit of immutability without necessarily paying a huge performance penalty. Analogy, the permanent ledger. Imagine a traditional accounting system where entries on a ledger could be erased and rewritten at any time. If there was a dispute over a balance, how would you verify it? It would be nearly impossible to trace the origin of a number if it could be randomly changed. Now, imagine an accounting system where every transaction is a new, uneditable entry. If you transfer money, a new withdrawal entry and a new deposit entry are added. You don't go back and modify the original balance entry. To find your current balance, you sum all the entries. If you need to correct a mistake, you add a new corrective entry. This immutable ledger provides a clear, auditable history. You can always trace exactly how any balance was arrived at. This is the power of immutability. Achieving immutability in practice, conceptually. How do you work with immutable data in practice? For simple values, instead of x equals 5, x equals x plus 1, which mutates x, you might conceptually have a new x-bluesone value that is x plus 1, leaving the original x as 5. For collections, lists, maps, instead of mylist add item, which changes mylist, you would have a function that returns newlist equals mylist with added item. The original mylist remains untouched. Rebuilding objects records. If you have a user record with name and email, and you want to change the email, you'd create a new user record with the updated email, copying over the existing name. This seemingly simple shift, from changing in place to creating anew, has profound implications for the clarity, reliability, and correctness of your software systems, especially as they scale and face the demands of concurrency. Immutability, combined with pure functions, forms a formidable pair that allows you to build incredibly robust applications on a foundation of certainty. Chapter 4. Functions as first-class citizens. The building blocks of flexibility. We've laid the groundwork with pure functions and immutability, which bring predictability and reliability to our code. Now, let's explore a concept that injects tremendous flexibility and expressive power into functional programming. Treating functions as first-class citizens. What does it mean for something to be a first-class citizen in the programming world? It means that functions are treated like any other ordinary value or piece of data, like numbers, strings, or true-false values. They can be assigned to variables. You can store a function in a named variable. Passed as arguments to other functions, you can give a function to another function to use. Returned as values from other functions. A function can generate and give back another function. Stored in data structures. You can put functions into lists, maps, or other collections. This might not sound revolutionary if you've already encountered programming languages that allow this. Many modern languages, including Python, JavaScript, Ruby, and even newer versions of Java, support first-class functions to varying degrees. However, in functional programming, this capability is not just a feature. It's a fundamental design principle that enables powerful patterns and abstractions. Analogy. Tools in a toolbox. Imagine you have a toolbox filled with various tools: a hammer, a screwdriver, a wrench. These tools are first-class citizens of your toolbox because you can assign them to a name. This is my hammer. Pass them to someone. Here, use my hammer. Ask someone to give you back a tool. Go to the shed and bring me back the best hammer for this job. Put them in a storage bin. All my hammers go in this drawer. Now imagine if hammering, the action, could also be treated like a tool. You could put the concept of hammering into a variable, give hammering instructions to someone else, or even have a factory that produces different kinds of hammering techniques as new tools. This is what it means for functions to be first class. They stop being just commands that run and become tangible things you can manipulate. Passing functions as arguments, callbacks, and customization. This is perhaps the most common application of first-class functions. When you pass a function as an argument to another function, the receiving function can then call back and execute the function you provided at an appropriate time. This enables incredible flexibility and allows you to customize behavior without rewriting large blocks of code. Conceptual example: sorting with custom logic. Imagine you have a list of people, each with a name and age. You want to sort this list. Sometimes you want to sort by name, sometimes by age. In a world without first-class functions, you might need two separate sorting functions: sort by name, list of people, and sort by age, list of people. With first-class functions, you can have a single, generic sort, list, comparison function. You then provide a small, specialized comparison function as an argument. To sort by name, you pass sort, list of people, function that compares names. To sort by age, you pass sort, list of people, function that compares ages. The sort function itself doesn't need to know how to compare names or ages. It just knows that it needs a way to compare any two items, and it relies on the function you provide to handle that specific comparison. This makes sort highly reusable and adaptable. Conceptual example: event handling. When you click a button on a web page, what happens? Typically, you register a piece of code, a function to be executed when the click event occurs. This function, often called a callback function, is passed as an argument to the button's event listener. The button's code then calls back to your function when the event happens, returning functions from other functions, factory functions, and closures. Just as functions can take other functions as input, they can also produce functions as output. This might seem a bit mind-bending initially, but it's hugely powerful for creating specialized functions on the fly or for building highly configurable systems. Conceptual example: creating specialized calculators. Imagine you want to create functions that always add a specific number. You could write addfiv x equals x plus 5, addn x equals x plus 10. But what if you wanted to generate these addn functions dynamically? You could have a function factory, makeHeader n. This is a function that takes a number n when you call it. It returns a new function that adds n to its input. Addfiv equals makeHeader 5. Now addfiv is a function that adds 5. Addn equals makeHeader 10. Now addn is a function that adds 10. This is an example where the inner returned function remembers the value of n from when it was created, even after makeHeader has finished running. This concept is often called a closure. Closures allow functions to capture the environment in which they were defined, giving them persistent access to outside variables. This enables powerful techniques for managing state and creating encapsulated behavior without relying on mutable objects. Storing functions in data structures, command patterns, and dynamic behavior. Because functions are just values, you can store them in lists, arrays, or maps, just like any other data. This allows for incredibly dynamic behavior. Conceptual example: a menu system. Imagine a simple text-based game where a menu presents options: start game, load game, settings. Instead of using a complex if-else-if block to check the user's choice and then manually call the corresponding action, you could store the actual action functions in a map. Menu actions equals start game function, load game function, settings function. When the user enters start, you just retrieve menu actions start and then call that function. This makes the system very extensible. Adding new menu options is as simple as adding a new entry to the map. The power of first-class functions, abstraction and composition, the ability to treat functions as flexible building blocks, lays the groundwork for some of the most elegant and powerful patterns in functional programming. Higher-order functions. This term refers to functions that either take other functions as arguments or return functions as results, or both. The sort and make-header examples above are classic higher-order functions. They allow you to abstract over common patterns of behavior, making your code more expressive and less repetitive. We'll explore these in much more detail in the next chapter. Composition. When functions are first class, you can easily combine them to make new, more complex functions. Think of it like snapping together multiple Lego bricks, each of which performs a small, well-defined task to build a larger structure. This functional composition is a hallmark of the FP style and leads to highly modular and readable code. In essence, by elevating functions to first-class citizen, status functional programming gains an extraordinary level of expressiveness and flexibility. It moves from merely executing commands to manipulating the logic itself, allowing developers to craft highly reusable, configurable, and elegant solutions to complex problems. This fundamental concept is the key that unlocks the door to many of the advanced functional patterns we'll explore. Chapter 5. Higher-order functions, orchestrating complexity with elegance. In the previous chapter, we discovered the power of treating functions as first-class citizens, being able to pass them around like any other piece of data. This concept isn't just a quirky feature. It's the very foundation for one of the most elegant and practical tools in the functional programmer's toolkit, higher-order functions. What exactly is a higher-order function? Simply put, a higher-order function is a function that does at least one of two things: takes one or more functions as arguments, returns a function as its result. If a function does either of these, it's a higher-order function. This isn't a complex, abstract idea. It's a very practical way to make your code more flexible, reusable, and expressive. Higher-order functions allow us to abstract away how we do something, letting us focus on what we want to achieve. Analogy: the specialized assembly line. Imagine an assembly line in a factory that processes raw materials into finished products. A map station. This station takes every item that passes through and applies a specific, pre-assigned transformation to it. Maybe it paints every item red or attaches a lid to every container. The key is it applies the same transformation to all. The actual painting or attaching is a function you give to the station. A filter station. This station examines every item and decides whether to let it pass or discard it. Maybe it only lets through items that are blue or items over a certain weight. Again, the rule for passing or discarding is a function you give to the station. A reduce station. This station takes all the items that have passed through so far and combines them into a single summary. Maybe it counts them, or adds up their weights, or concatenates their labels. The method of combining is a function you provide. These stations themselves are higher order because they don't do the detailed work directly. They orchestrate it by using a specialized function you plug into them. 3 common higher order functions: map, filter, and reduce, fold. These 3 are the workhorses of functional programming when dealing with collections of data. They represent common patterns of data transformation that are often found in software development, regardless of the specific problem domain. 1 map, transforming every element. Purpose: to transform each element in a collection, like a list or array, into a new element, producing a new collection of the same length. Think of it as applying a specific operation to every item individually and collecting all the results. How it works conceptually: you have a list of items, item 1, item 2, item 3. You provide a transformation function, e.g., square a number, make uppercase. Map applies your transformation function to item 1, then to item 2, then to item 3. It collects all the results into a brand new list. Transform at item 1, transform at item 2, transform at item 3. Importantly, the original list is not changed. Remember immutability. A new list is created. Everyday analogy. You have a shopping list of ingredients, and you want a new list that shows the price of each ingredient. The price check action is your transformation function. You map that function over your list of ingredients to get a new list of prices. Conceptual example, original data. 1, 2, 3, 4, a list of numbers. Transformation function, double number, which returns number 2. Map double 1, 2, 3, 4 would produce 2, 4, 6, 8. 2. Filter, selecting specific elements. Purpose, to create a new collection containing only the elements from the original collection that satisfy a certain condition. How it works conceptually, you have a list of items. Item 1, Item 2, Item 3, Item 4. You provide a condition function, often called a predicate function, that takes an item and returns true or false, e.g., Eisvin, isadult. Filter applies your condition function to Item 1. If true, it keeps Item 1. If false, it discards it. It does this for all items. It collects all the kept items into a brand new list, kept item A, kept item B. The new list will be the same length or shorter than the original. Again, the original list is not changed. Everyday analogy, you have a pile of clothes and you want to gather only the red shirts. The "is it a red shirt?" question is your condition function. You filter your pile of clothes using this function to get a new pile containing only red shirts. Conceptual example, original data. 1, 2, 3, 4, 5. Condition function, Eisvin number which returns true if number is even, false otherwise. Filter, Eisvin 1, 2, 3, 4, 5 would produce 2, 4. 3. Reduce or fold, aggregating elements into a single result. Purpose, to combine all elements in a collection into a single result. This can be a sum, a product, a single string, or any other aggregated value. How it works conceptually. You have a list of items. Item 1, Item 2, Item 3, Item 4. You provide a combining function, e.g., add numbers, concatenate strings. This function takes 2 arguments, the current aggregated total, often called accumulator, and the next item from the list. You also usually provide an initial value for the accumulator, e.g., 0 for summing, for concatenating. Reduce starts with the initial value. It applies the combining function using the initial value and the first item, then uses that result and the second item, and so on until all items are processed. The final output is that single, aggregated result. Everyday analogy, you have a basket of various fruits and you want to know their total weight. The add weight action is your combining function. You reduce your basket of fruits by starting with an initial weight of 0 and adding each fruit's weight to the running total. Conceptual example, original data, 1, 2, 3, 4. Combining function, add accumulator, number, which returns accumulator plus number. Initial value, 0. Reduce, add 0, 1, 2, 3, 4. Add 0, 1 equals 1. Add 1, 2 equals 3. Add 3, 3 equals 6. Add 6, 4 equals 10. Would produce 10, the sum of the list. Chaining higher order functions, the power of composition. The true elegance of map, filter, and reduce comes from their ability to be chained together. Because each of them takes a list and returns a new list, or a single value for reduce, you can string them into a pipeline of operations, transforming data step by step. Conceptual example, processing user data. Imagine you have a list of user records, and you want to find the sum of ages of all adult users. First, you filter the list to keep only users who are adults, using an isadult function. Then, from that filtered list, you map each user record to just their age, using a getAge function. Finally, you reduce the list of ages to their sum, using an add function with an initial value of 0. This sequence of operations is clear, readable, and highly modular. Each step is a pure function, operating on immutable data, resulting in a predictable transformation. No intermediate variables are mutated, and the logic flows cleanly. Beyond map, filter, and reduce, while these 3 are the most common, the concept of higher-order functions extends far beyond them. Functions can memoize another function, a higher-order function that takes a function as input and returns a new function that caches the results of the original function's calls. Query a function. Transform a function that takes multiple arguments into a sequence of functions, each taking a single argument. Compose functions. Take two functions, say f and g, and return a new function that represents f applied to the result of g. Higher-order functions are not just an academic curiosity. They are immensely practical tools that allow you to express complex data transformations and behaviors concisely and elegantly. They encourage a declarative style of programming, where you describe what you want to achieve rather than how to achieve it, making your code easier to read, test, and maintain. They are truly the orchestrators of complexity in the functional paradigm. Chapter 6. Recursion, Mastering Repetition Without Loops. If you're accustomed to imperative programming, you're likely very familiar with loops. For loops, while loops, do while loops. These constructs tell the computer to repeatedly execute a block of code, often relying on a mutable counter or a changing condition. In functional programming, while loops aren't strictly banned, the preferred and often more natural way to handle repetition is through recursion. Recursion is the process where a function calls itself to solve a problem. It's like looking up a word in a dictionary, only to find the definition uses another word you don't know, so you look that one up too. You keep looking words up until you find one whose definition you do understand, at which point you can work your way back up. The two pillars of recursion, base case and recursive step. Every recursive function fundamentally relies on two parts. The base case, this is the stopping condition. It's the simplest version of the problem that can be solved directly without any further recursion. Without a base case, a recursive function would call itself indefinitely, leading to an error, often a stack overflow. The recursive step. This is where the function calls itself, but for a smaller, simpler version of the original problem. The idea is that each recursive call brings you closer to the base case until the problem is trivial enough to solve directly. Analogy: Matryoshka dolls and Russian nesting dolls. Imagine a set of Matryoshka dolls. The problem: you want to find the tiny, innermost doll. The recursive step: you pick up a doll. If it's not the smallest one, you open it up to find a smaller doll inside. You then apply the same process to that smaller doll. The base case. Eventually, you open a doll and find that it is the smallest one. You can't open it further. At this point, you've solved the problem for that doll, and you simply return it. Once you find the innermost doll base case, you effectively return from that call, then from the one that contained it, and so on, until you've fully returned from the initial call and presented the innermost doll. Conceptual example: calculating factorial. Let's use a classic example: calculating the factorial of a number. The factorial of a non-negative integer n, denoted as n, is the product of all positive integers less than or equal to n5. Equals 54321 equals 120. By definition, 0 equals 1. How would we define this recursively? Base case: if the number is 0, the factorial is 1. This is our stopping point. Recursive step: if the number n is greater than 0, the factorial is n multiplied by the factorial of n1. Notice how factorial n1 is a smaller version of the original problem. Conceptually, a factorial function would look like this. Factorial n: if n is 0, return 1 base case. Else return n factorial n1 recursive step. Let's trace factorial 3. Factorial 3 is 3 equal to 0? No, so 3 factorial 2. Factorial 2 is 2 equal to 0? No, so 2 factorial 1. Factorial 1 is 1 equal to 0? No, so 1 factorial 0. Factorial 0 is 0 equal to 0? Yes. Return 1 base case reached. Now the results unwind back up the chain. Factorial 1 now has 1 1 because factorial 0 returned 1 equals 1. Factorial 2 now has 2 1 because factorial 1 returned 1 2. Factorial 3 now has 3 2 because factorial 2 returned 2 equals 6. And finally, 6 is the result for factorial 3. Recursion versus loops, a shift in perspective. Why favor recursion in functional programming? No mutable state. Loops often rely on mutable counters, I equals I plus 1, or conditions that change state, continue loop equals false. Recursion, especially pure recursion, avoids this. Each call generates its own context, and the accumulated result is passed along or built up through the return values, rather than modifying external variables. This aligns perfectly with the principle of immutability. Clarity for certain problems. For problems that are naturally defined in terms of smaller, self-similar subproblems, like tree structures, mathematical sequences, or even list processing, recursion can provide a much clearer and more concise expression of the logic than an iterative loop. It often mirrors the mathematical definition directly. Mathematical elegance. Functional programming draws heavily from mathematics. Many mathematical definitions, like factorial, are inherently recursive, so representing them directly in code feels very natural. Tail recursion, an optimization for performance. One common concern with recursion, especially in languages not optimized for it, is that each recursive call adds a new frame to the program's internal call stack. If the recursion goes too deep, this can lead to a stack overflow error, running out of memory for the call stack. Iterative loops, conversely, don't typically consume extra stack space beyond a fixed small amount. However, many functional programming languages, and compilers for other languages when configured correctly, offer an optimization called tail call optimization, TCO, or tail recursion optimization. What is tail recursion? A function is tail recursive if the recursive call is the very last operation performed in the function before it returns. There's nothing else to do after the recursive call finishes. In our factorial, n equals n factorial, n1 example, factorial, n1 is called, and then its result is multiplied by n. The multiplication is the last operation the current call performs. This is not tail recursive. To make it tail recursive, you often introduce an accumulator argument that carries the intermediate result. Factorial tail recursive, n accumulator. If n is 0, return accumulator. Else return factorial tail recursive, n1 accumulator n. Notice now that the recursive call factorial tail recursive, n1 accumulator n, is the very last thing that happens before the function returns. The current n is multiplied into the accumulator before the next recursive call. Why TCO matters conceptually. When a function is tail recursive, a smart compiler can optimize it by effectively transforming the recursion into an iterative loop behind the scenes. Instead of adding a new stack frame for each call, it reuses the current frame, eliminating the risk of stack overflow and making it as efficient as a loop. This means that in functional programming, you can often write naturally recursive code for clarity and maintainability, and rely on the compiler to turn it into an efficient, loop-like execution. Practical considerations, and when to choose recursion. While recursion is powerful, it's not always the immediate choice for every repetitive task. Sometimes, a simple map or filter on a collection, which conceal their own internal iteration, is more appropriate and readable than a custom recursive function. However, for problems that inherently involve self-referential structures, like traversing a tree data structure, processing nested lists, or algorithms defined recursively, pure recursion offers beautiful elegance and clarity. It allows you to think about breaking down a problem into a smaller version of itself, leading to solutions that are often shorter, more understandable, and free from the mutable state that can plague imperative loops. Mastering recursion is a fundamental step in truly embracing the functional way of thinking. Chapter 7, Managing State, Errors, and Side Effects, the FP Way. So far, we've explored the core tenets of functional programming: pure functions, immutability, first-class functions, higher-order functions, and recursion. These principles emphasize predictability, reliability, and the absence of side effects. But wait, you might ask, how can a program truly be useful if it can't change anything, manage state, handle problems' errors, or interact with the outside world, side effects like input-output? The answer is that functional programming doesn't eliminate these necessities. It tackles them with a different, more disciplined approach. The functional approach to state, embracing immutability's flow. In imperative programming, state typically refers to the values of all variables and data structures at a given moment. Managing state often involves directly mutating these variables. When you update a user's profile, you literally go into the user object and change its address field. This mutation can be a source of bugs, especially in concurrent systems, as we discussed in the immutability chapter. Functional programming fundamentally shifts this perspective. Rather than modifying existing state, It embraces the idea of transforming one state into a new state. No variable reassignment, conceptually. Imagine you have a number x and you want to increment it. In an imperative style, you might write x equals x plus 1. This changes the value that x points to. In a functional style, you would think, I want a new number that is x plus 1. You might call this new number y or next x. The original x remains unchanged. Original, current balance equals 100. Functional update, new balance equals current balance plus transaction amount. The new balance is a distinct, immutable piece of data. Current balance still holds its original value of 100. Transforming data structures. When adding an item to a list or updating an entry in a map, you don't modify the original collection. Instead, you create a new collection that incorporates the change, perhaps sharing underlying data structures efficiently, as discussed with persistent data structures. Instead of shopping list add, milk, you'd conceptually get newshopping list equals shopping list with item, milk. This doesn't mean your program stays static. It means the sequence of changes is represented by a series of immutable states, each derived from the previous one by applying a pure function. It's like a chain of snapshots, where each snapshot is a complete, unchangeable record of a moment in time. This approach makes reasoning about the flow of data and changes significantly easier, especially in complex applications. Analogy, the immutable ledger revisited. Think back to the financial ledger analogy. Instead of erasing and rewriting entries, mutation, every single transaction is a new, immutable line item. Your balance isn't a single mutable number. It's the result of calculating the sum of all entries up to a certain point. When a new transaction occurs, you don't adjust the old transactions, you simply add a new line. Your state, the current balance, is always a derivation from the series of immutable facts. Managing errors, embracing explicit success or failure. Traditional imperative programming often relies on exceptions for error handling. An exception interrupts the normal flow of the program, jumping to a special error handling block. While useful, exceptions can be seen as a form of non-local side effect. A function might unexpectedly throw an exception, breaking pure function principles. Functional programming favors more explicit and predictable ways of handling errors, often by making error conditions part of the function's return value. The idea is to make success or failure an expected outcome of a function, rather than an unpredictable disruption. Conceptual example, the optional or result type. Instead of a find_user_bid function, either returning a user or throwing an exception if the user isn't found, it might return a special container that clearly indicates one of two possibilities. Success, the container holds the found user. Failure, the container holds nothing or perhaps an error message. This container type is often called an optional or maybe, if it strictly holds a value or nothing, or a result or either, if it holds a success value or an error value. Look a product producted, if product found returns result, success, product object. If product not found returns result, error, product not found. The calling code then explicitly checks the result container. If it's a success, use the product, otherwise display the error. This forces you to handle both success and failure pathways directly in your code, preventing unexpected crashes and making function outcomes transparent. It's like a package from a delivery service. It either contains your item or a note explaining why it couldn't be delivered, but it always arrives with a clear status. Containing side effects. The boundaries or impure core approach. As stated before, realistic programs must have side effects. They need to interact with databases, display information to users, pull data from the internet, and so on. Functional programming doesn't eliminate these. It aims to isolate and contain them. Think of your program as having a pure, functional core that does all the heavy lifting of computation and data transformation. This core is built with pure functions operating on immutable data, making it highly reliable and testable. Around this pure core, you have a thin wrapper, or boundary, layer responsible for interacting with the outside world. This layer contains the impure functions that perform I/O, interact with external systems, or manage mutable state where absolutely necessary, e.g., in a small, contained part of a user interface. Analogy. The clean room factory. Imagine a factory where highly sensitive components are manufactured in a pristine, clean room environment. Inside, everything is precise, predictable, and doesn't contaminate anything. This is your pure functional core. However, raw materials need to enter the clean room, and finished products need to leave. This happens through special airlocks and transfer stations. These stations are your boundary functions. They interact with the messy, impure outside world, but they do so in a controlled way, ensuring that the purity of the clean room is maintained. How this isolation works: conceptual. Pure core, all data transformations, complex business logic, and calculations happen here. These functions are easy to unit test and reason about. Example: calculate order total, items, discount code, purely calculates a number. Example: generating voice data, order details, purely transforms data into an invoice structure. Impure boundary. Functions that interact with the user, database, or network live here. They call the pure core functions to do the actual processing. Example: read order from database, ordered, reads data, side effect. Example: display invoice user, invoice data, prints to screen, side effect. Example: process user input string, gets input, side effect. A common pattern is that the main entry point of your program will often be an impure function that orchestrates the flow. It gets input, impure, passes it to pure functions for processing, and then outputs the result, impure. This clear separation allows you to maximize the benefits of functional programming where it matters most, in your core logic, while still building practical, interactive applications. By consciously managing state through immutable transformations, handling errors as explicit values, and containing side effects to the edges of your system, functional programming provides a powerful framework for building robust, understandable, and less error-prone software, even in the face of complex interactions with the real world. This disciplined approach is a significant part of the predictable path. Chapter 8, Composition and Conciseness, Weaving Logic Together. We've explored the individual strengths of functional programming: pure functions, immutability, first-class functions, and higher-order functions. Now, let's see how these elements beautifully converge through the practice of composition. In functional programming, your functions are like interchangeable Lego bricks. You can snap them together in powerful and elegant ways to build complex structures. What is composition? The Lego analogy. In its simplest form, function composition means combining two or more functions to create a new function. If you have a function f and a function g, composing them means creating a new function that first applies g to its input, and then applies f to the result of g. It's like a pipeline. Input goes into g, its output becomes the input for f, and f's output is the final result. Analogy: Lego bricks. Imagine you have a small Lego brick that changes a red piece into a blue piece, make blue function. You have another small Lego brick that attaches a wheel to a piece, add wheel function. You can compose these. You could say, first make blue, then add wheel. The result is a new, single instruction that takes a piece, makes it blue, and attaches a wheel. You don't need to describe the steps inside. You just use the new combined instruction. Each individual Lego brick, pure function, is simple, predictable, and does one thing well. When you combine them, you build highly complex structures without adding complexity to the individual parts. This modularity is a hallmark of functional programming. Why composition matters. Benefits of weaving functions. The emphasis on composition brings several significant advantages: readability and clarity. When you compose functions, you often read the code like a declarative sentence, describing what you want to do rather than how to do it. Instead of a series of sequential, state-changing steps, you see a clear flow of data transformations. Compare. Take numbers, loop through them, double each one, then loop again and filter out evens. 2. Numbers, then map double, then filter isven. The latter focuses on the operations themselves. Reusability. Small, pure, composable functions are highly reusable. A double function can be used in countless contexts, not just when mapping over a list. This reduces code duplication and creates a rich library of reliable building blocks. Modular design. Complex problems are broken down into smaller, manageable subproblems, each handled by a dedicated, pure function. These functions can then be combined, allowing you to build intricate logic from simple, well-understood components. It's like designing complex machinery from standardized screws, gears, and levers. Testability, again. Since each component function in a composition is pure and isolated, you can test it independently. If the overall composition produces a bug, you can quickly narrow down which component function is misbehaving. Maintainability. When logic is composed, it's easier to understand, debug, and modify. If you need to change a specific transformation, you update or swap out a small, isolated function rather than wading through a large, intertwined block of code. Pipelining data. From imperative steps to declarative flow. Let's revisit an imperative vs declarative example to really drive home the conciseness and clarity that composition brings. Imperative style, focus on how. Imagine you have a list of raw transaction strings, 100 USD, 25 EUR, 75 USD. If you wanted to process only the USD transactions, convert them to EUR, filter for large amounts, and then format them for display, an imperative approach might look something like this sequence of thoughts. Processed transactions, initial empty list. For each transaction string in raw transactions, step 1, parse and extract. Amount equals parse a number, transaction string. Currency equals extract currency, transaction string. Step 2, filter for USD. If currency equals USD. Step 3, convert to AUR assuming exchange rate is known. Converted amount equals amount us to rate. Step 4, filter for large amounts. If converted amount 50, step 5, format for display. Formatted item equals format for display, converted amount. Add to the result list. Add formatted item to processed transactions. Now processed transactions holds the final result. This style explicitly describes each step, often relies on a mutable processed transactions list, and might pull in external mutable state, us to rate. It tells the computer how to iterate and manage state. Functional/composed style, focus on what? In a functional approach, we'd first ensure we have our small, pure functions ready. Parse amount, string. Takes 100 USD, returns 100. Extract currency, string, takes 100 USD, returns USD. Isust, currency string, returns true if USD. Convertistor amount. Returns amount fixed rate, this would be a pure function. The rate would ideally be an input, or the function would capture it immutably. Is greater than 50 or amount, returns true if amount 50. Format for display amount, returns amount. XEUR. Now, we can clearly express the transformations as a pipeline using higher-order functions like map and filter that we learned in Chapter 5. Imagine our raw transactions list is 100 USD, 25 EUR, 75 USD. Filter to only USD transactions. US transactions equals filter. Transaction string equals isust, extract currency, transaction string, raw transactions. Conceptually, this gives us 100 USD, 75 USD. Map to convert remaining amounts to EUR. EUR amounts equals map. Transaction string equals convertistor, parse amount, transaction string, US transactions. Conceptually, this results in 92.00, 69.00, assuming 1 USD equals 0.92 EUR. Filter for amounts greater than 50 EUR. Large EUR amounts equals filter, is greater than 50 or EUR amounts. Conceptually, this yields 92.00, 69.00, as both are greater than 50. Map to format for display. Final display list equals map, format for display, large EUR amounts. Conceptually, the final result is amount 92.00 EUR, amount 69.00 EUR. While the explicit steps above make it verbose, in a language supporting a fluent functional style, this entire chain of operations could condense dramatically to something like final display list equals raw transactions filter, map, filter, map. This concise, chainable style is a direct result of strong support for first-class functions, pure functions, and immutable data, allowing these higher-order operations to flow seamlessly. Each operation takes an immutable collection and produces a new immutable collection, creating a clear and predictable transformation pipeline. Conciseness through abstraction. Functional programming naturally leads to concise code, not by making it cryptic, but by providing powerful abstractions. Instead of rewriting loops and managing temporary variables for every data transformation, you can leverage map, filter, reduce, and other higher-order functions. These functions encapsulate common patterns, allowing you to express complex ideas very compactly. When you read data filter, isvalid, map, process, you immediately understand the intent. Take the valid data and then process each item. This is far more expressive than delving into the mechanics of loops and conditional checks required by an imperative approach. This chapter underscores that functional programming is not just about isolated concepts, it's about how these concepts interlock. Composition is the grand orchestrator, allowing you to weave together small, predictable units of logic into powerful, expressive, and easily manageable software solutions. It makes your code not just work, but sing. Chapter 9, Functional Programming in the Real World, Beyond the Theory. We've covered the theoretical underpinnings and core concepts of functional programming. You might now be thinking, this all sounds great for calculations and academic problems, but how does it apply to building real-world applications? Do people actually use this stuff? The resounding answer is absolutely yes. Functional programming concepts are increasingly permeating software development across various domains, often in subtle ways you might not even notice. Where functional concepts are flourishing, functional programming isn't limited to esoteric academic languages. Its principles are being adopted and integrated into mainstream programming, solving practical problems in diverse industries. Mainstream languages embracing FP. Many popular languages, originally designed primarily for imperative or object-oriented programming, have incorporated significant functional features. This allows developers to adopt functional styles without completely abandoning their existing toolchains. JavaScript. Historically known for its liberal approach to side effects, JavaScript has embraced functional paradigms heavily, especially in modern front-end development frameworks. Libraries like React, known for its component-based UI, heavily leverage immutability. State updates create new state objects, and pure functions. Components ideally render predictably given their props and state. Many JavaScript developers use map, filter, and reduce regularly for data transformation. Python. While multi-paradigm, Python supports first-class functions and includes built-in constructs like map, filter, and reduce, though reduce requires importing from functools. It's commonly used by data scientists and engineers who appreciate the clarity and expressiveness of functional transformations on data for analysis and processing. Java and C#. Both languages have introduced lambda expressions, allowing anonymous functions to be treated as first-class citizens, and stream processing APIs. These features enable developers to write more concise and functional-style code for processing collections of data, moving away from verbose imperative loops and enhancing readability. Go, while not a purely functional language, Go emphasizes concurrency and often encourages practices that align with FP principles, such as minimizing shared mutable state and favoring explicit data passing between concurrent components. Languages built for or heavily influenced by FP. Some languages are designed from the ground up with strong functional foundations, often pushing the boundaries of what's possible with FP. Haskell, a purely functional language known for its strong type system and deep academic roots. While perhaps not widely used for mainstream enterprise applications, it's a powerful research language and continues to influence the design of many other languages and functional programming patterns. Scala runs on the Java Virtual Machine, JVM, and is a multi-paradigm language that seamlessly blends object-oriented and functional programming. It's popular in big data, e.g., Apache Spark, a widely used data processing framework, is written in Scala and highly concurrent distributed systems. Clojure, a Lisp dialect running on the JVM. It deeply embraces immutability and functional programming, known for its emphasis on conciseness, powerful data structures, and robust concurrency features. Elixir/Erlang. Born from the telecommunications industry, these languages are built for highly concurrent, fault-tolerant systems, e.g., used for WhatsApp's backend, handling millions of simultaneous connections. They are inherently functional, designed to handle massive numbers of independent operations without crashing, directly leveraging FP's strengths in concurrency. F#, Microsoft's functional first language, running on the .NET platform. It integrates well with existing .NET libraries, allowing a gradual adoption of functional practices within an existing ecosystem, making it accessible to many enterprise developers, where functional programming solutions excel. The strengths of FP lend themselves particularly well to certain problem domains: concurrency and parallelism. This is arguably FP's most significant advantage in today's multi-core, distributed computing landscape. With immutable data and pure functions, the common headaches of multi-threaded programming race conditions, deadlocks, and corrupted shared state largely disappear. It's much simpler to write code that safely leverages multiple CPU cores or distributes work across many machines. This is critical for building scalable systems, from web servers to complex data processing pipelines. Big data and data processing. When dealing with large datasets, transformations need to be reliable, predictable, and scalable. The map, filter, and reduce patterns are fundamental operations in big data processing frameworks like Apache Spark and Hadoop, providing a clear, composable way to process massive amounts of information. The inherent immutability ensures data consistency and integrity across distributed operations. User interface, UI development. Modern UI frameworks, especially in the web front-end world, like React in JavaScript, and some purely functional approaches, like Elm, heavily use functional principles. UI components are often treated as pure functions of their inputs, properties or props, and internal state, leading to UIs that are easier to reason about, test, and debug. When a user interacts with the application, the UI simply transforms from one predictable functional state to another, rather than relying on complex direct DOM manipulations. Scientific computing and financial modeling. In fields where correctness, precision, and verifiability are paramount, such as scientific simulations, numerical analysis, and financial calculations, the emphasis on pure functions and predictable outcomes makes functional programming an excellent fit. Algorithms can be expressed in a way that closely mirrors their mathematical definitions. Compilers and interpreters. The transformation of code from one format to another, parsing, abstract syntax tree manipulation, code generation, is inherently a functional problem. Many programming language tools and compilers lean heavily on functional patterns, due to the clarity and composability they offer for complex data transformations. Benefits in a team environment. Aside from the technical advantages, adopting functional principles brings significant benefits to software development teams. Easier code reviews. Pure functions are self-contained and don't affect external state, making them easier to understand and review in isolation. Reviewers don't need to juggle complex mental models of mutable state or side effect chains. Reduced bug count. The elimination of unintended side effects and mutable shared state naturally leads to fewer subtle, hard-to-trace bugs. Many common classes of errors, like race conditions or unexpected data changes, are simply designed out of the system. Improved maintainability. Composable, modular functions are easier to refactor, upgrade, and extend without inadvertently breaking existing functionality. Changes are localized, reducing the ripple effect of modifications. Addressing challenges and misconceptions. While powerful, FP is not without its considerations. Understanding typical concerns can help in its adoption. Learning curve. Shifting from an imperative mindset to a functional one can be challenging initially. Concepts like recursion and thinking about data transformations rather than step-by-step instructions require practice and a different way of problem solving. Performance, perceived versus real. The idea of creating new copies with immutability sometimes raises performance concerns. However, modern functional languages and libraries are highly optimized, e.g., with persistent data structures and tail call optimization, such that this often isn't a practical issue for most applications. For truly performance-critical sections, e.g., intense numerical computation, hybrid approaches or specific optimizations can be used. I/O and side effects. As discussed, handling interactions with the impure, outside world, databases, network requests, user input, requires specific patterns to keep the core logic pure. This can feel abstract initially, but leads to cleaner architectural separation for managing these necessary complexities. The hybrid approach, mixing paradigms. Perhaps the most common way functional programming is integrated into the real world is through a hybrid approach. Many successful projects combine the strengths of object-oriented, imperative, and functional paradigms. You might have an object-oriented structure where objects primarily hold state, but the methods that operate directly on that state or transform it are written in a pure, functional style. Or you might use functional pipelines, like map, filter, and reduce, for all data transformations within an otherwise imperative codebase. Functional programming is no longer a niche, academic pursuit. Its principles are proving to be invaluable tools for tackling the complexity of modern software. By understanding and selectively applying its concepts, developers and teams can build more robust, scalable, and manageable applications, truly navigating the predictable path in the ever-evolving landscape of technology. Chapter 10, Embracing the Predictable Path, Your Journey Forward. We've journeyed through the core concepts of functional programming, from the foundational purity of functions and the unwavering consistency of immutability, to the flexible power of higher-order functions and the elegant repetition of recursion. We've seen how these ideas compose into concise, readable logic and how they are applied in diverse real-world scenarios. Now, as we stand at the end of this book, it's time to consolidate what we've learned and look ahead at your continued exploration. The core promise: predictability, reliability, scalability. If there's one message to take away from the predictable path, it's that functional programming fundamentally aims to make software more predictable. This predictability stems from its core tenets: pure functions, they are mathematical machines. Same input, same output every time. No surprises, no hidden influences. This makes testing trivial and reasoning about code straightforward. Immutability: data, once created, is fixed. This eliminates entire classes of bugs related to unexpected modifications, simplifies concurrency, and makes debugging a clear audit trail. Composition: building complex systems from small, pure, predictable functions, like snapping Lego bricks together, leads to modular, reusable, and easy-to-understand code. Focus: state management. While programs must manage state and side effects, FP encourages isolating these chaotic aspects to the edges of your system, keeping your core logic clean, reliable, and testable. These principles combine to create software that is not only less prone to bugs, but also significantly easier to scale in terms of both team size and computational demands. When every part of your system has clearly defined inputs and outputs and doesn't interfere unexpectedly with other parts, collaboration thrives and parallel processing becomes a walk in the park. Addressing common myths and fears. As with any paradigm shift, functional programming sometimes faces misconceptions that can hinder adoption. Let's dispel a few. It's too academic complex for real-world development. While some advanced theoretical concepts can be academic, the core principles we discussed: pure functions, immutability, composition, are incredibly practical. As Chapter 9 demonstrated, these ideas are successfully applied daily in mainstream languages and major companies. Simplicity comes from reducing side effects and managing state explicitly, not from introducing complexity. It's slow because you're constantly copying data. This is rarely a practical concern. As mentioned, modern functional languages and libraries employ highly optimized techniques, like persistent data structures and tail call optimization, that make these operations efficient. The performance gains from easier concurrency and fewer bugs often far outweigh any theoretical overhead from copying. For critical performance bottlenecks, hybrid approaches allow you to switch to imperative optimizations if absolutely necessary. I can't do I/O or interact with databases in functional programming. This is incorrect. Functional programming provides disciplined ways to handle side effects. You isolate them to specific parts of your code, ensuring that your core business logic remains pure and testable. It's about managing side effects intelligently, not eliminating them. your journey forward. Embracing functional thinking. You don't need to dive headfirst into a purely functional language like Haskell to begin applying functional principles. Many modern languages offer fertile ground for experimenting with FP. Start small, practice often. Focus on pure functions. In your existing projects, identify opportunities to write small, pure functions. Can a helper function compute a value without changing anything outside itself? Can it accept all its inputs and produce a single output? Embrace immutability. Instead of modifying existing lists, try creating new ones with map and filter. See if you can transform data into new versions rather than updating old ones. Use higher-order functions. Look for places where you're writing loops to transform or filter collections. Can map, filter, or reduce simplify that code? Experiment with your current language's FP features. If you're a JavaScript developer, lean into array.prototype map, filter, reduce, and for each. Explore functional libraries like Lambda. If you're a Pythonista, practice with map, filter, functools, reduce. If you're using Java or C#, explore their stream APIs and functional interfaces. Read and explore. The world of functional programming is vast and rich. Look for resources specific to applying FP concepts in languages you already know. Gradually explore more advanced topics like functors, monads, often simplified as computational contexts, or category theory if your curiosity takes you there. However, remember that you don't need to understand these to gain immense benefits from the core ideas. Consider a dedicated functional language, eventually. If you truly enjoy the paradigm, consider dipping your toes into a language built from the ground up for functional programming, such as Elixir, F#, Clojure, or Scala. They offer a deeper immersion and truly demonstrate the power of the paradigm. A hybrid future for software development. The future of software development isn't necessarily a winner-take-all battle between paradigms. Instead, it's likely a hybrid landscape. Object-oriented and imperative approaches will continue to be vital, but they will increasingly be infused with functional techniques. You might design your system with objects holding state, but the methods that operate on that state will be pure functions transforming it. You might use functional pipelines for complex data transformations within a larger imperative application. By understanding functional programming, you're not just adding another tool to your belt, you're gaining a new mental model for approaching software design. You'll begin to see problems through a different lens, enabling you to write code that isn't just correct, but is also elegant, clear, and resilient to the inevitable complexities of modern systems. You've taken the first step on the predictable path. Keep exploring, keep learning, and keep building software that you can truly trust. The journey to more reliable, understandable, and scalable code has just begun.